Properties of triangle, sine rule. In this session, we'll see what sine rule is and how it is related to triangles. We'll also look into the derivation of the sine rule for different type of triangles like acute angle triangle, right angle, and obtuse angle triangle. Along with that, usage of the sine rule to find different elements of a triangle. Elements of a triangle are like the angles or the length of the sides. Coming to the sine rule, it states that in any triangle ABC, say here ABC is a triangle wherein the capital A, capital B, and capital C represent the vertices. Small a, small b, and small c represent the sides opposite to these vertices. In that case, the rule can be stated as small a upon sine A is equal to small b upon sine B is equal to small c upon sine C equal to 2r. The capital R is nothing but the circumradius. To understand this concept, first we should have basic knowledge about the trigonometric ratios, along with that circles and how circles and triangles are related with each other, like circumcircle concept is required. Along with that, different properties of a circle like chords. We have theorems related to chords and the angles that a chord make in different segments, how these angles will be related. All these concepts, we should be aware of those before starting into this. Now, let us consider any triangle. Acute angle triangle means when all the angles are less than 90 degrees, it is acute angle triangle. Here we have the figure. Now the side opposite to capital A vertex is BC. The same BC side, when written in capital letters, we have to use both the letters B and C, the vertices, to show the opposite side, or this can also be written as small a. In similar way, the side opposite to vertex B can be represented as small b, side opposite to C vertex can be represented as small c. So now pictorially it can be shown like this. Once we know what this capital A and capital C are, we will start deriving the formula. But along with this, we also have to know about a circumcircle. When we draw a circle passing through all these three vertices of a triangle, it is called as a circumcircle, and the circumcircle will have a center which will be represented as S. Now, this center, as all the vertices are lying on the circle, will be equidistant from all the vertices. Now, we have the center. To derive this formula, first let us consider the BC chord. Here, BC is a chord because it is joining two different points on the circle. And with respect to BC, angle BAC is the angle made by chord in the major segment of the circle. Now let us draw another angle using BC chord in such a way that one of the arms of the angle passes through the center S. So let us join C to S and from there to the circle. And this point is D. Join B and D. Means now BC chord has made another angle in the major segment, that is angle BDC. According to the statement that we have, the angles made by a chord at different points on the same side of the chord within a circle are equal. Using this statement, we can write angle BAC is equal to angle BDC. These two angles are made by the chord BC. Now, when we consider the chord DC, it is passing through the center, which means DC is the diameter. When the diameter is considered, and with that, if we make angle in any of the segments, diameter cuts a circle into two semicircles. So when it makes an angle in any of the segments, that angle would be 90 degrees. So statement is the angle made by a diameter in a semicircle is always 90 degrees. Because of that, this DC chord is making here angle this will be 90 degrees. That is angle DBC is 90 degrees. Now, in this right angle triangle using trigonometric ratios, and we also know that this is a circumcenter. DS is R, capital R, that is the circumradius. In similar way, CS is also R, that is the circumradius. Distance from the center to any point on the circle is circumradius denoted by capital R. So this is ds is R, and then CS is also R, which means DC is equal to ds plus SC. So that is R plus R, which is 2R. So considering this triangle BDC, for angle this BDC, we are again considering the angle BDC. For that, if we take sine, that is sine angle BDC is equal to, we know that sine of any angle is opposite divided by hypotenuse. Here the side opposite to D is this BC, which is nothing but A here. So this can be written as A upon hypotenuse here is DC. But here we know that DC is equal to 2R. So we got here sine BDC is A upon 2R. But from this equation, what we have, angle BDC is nothing but angle BAC. That is sine angle BAC is equal to A upon 2R. But angle BAC is nothing but angle A for the ABC triangle. So we can write this as sine A is equal to A upon 2R, or if we change this, we can write 2R is equal to A upon sine capital A. So in this way, we can prove for angle A. In a similar way, if we consider this chord AC, and using that, if we draw another chord passing through A and the center of the circle, it will make another angle. Now this AC chord has made two angles in the major segment. One is angle ABC and the second one is, let us take this point to be E, then it is AEC. So AC chord has made two angles in the segment and both the angles have to be equal. Also, we know that AE is the diameter, and in that case, there is angle ACE is the angle made by the diameter in the semicircle, so it will be equal to 90 degrees. So, considering the triangle AEC, if we take sine of angle AEC, that is for this particular angle, if we take the sine, it is opposite upon hypotenuse. The side opposite to angle AEC here is B, small b, upon hypotenuse here is this AE. Again, from A to S it would be R, and S to E also it would be R, because it's a circumradius. So AE can be written as R plus R to R. And we know that angle AEC is nothing but angle ABC from the first statement. So sine angle ABC can be written as B upon 2R. For triangle ABC, sine angle ABC can be written simply like angle B. So this is equal to B upon 2R. Now on rearranging this, we can write 2R is equal to B upon sine B. Consider chord AB to prove for angle C. Now chord AB is making angle ACB in the major segment. We'll draw another angle which passes through the circumcenter. So one of the arms has to pass through circumcenter. We'll draw from B to S and then we'll join onto the circle. From that point, we'll draw to point A. This is F. Now AB is making another angle in the circle, that is angle AFB. According to the chord's theorem, we have these two angles equal to one another. BF is the diameter, so BF will make angle 90 degrees in the segment, which means that angle BAF is equal to 90 degrees, making the triangle BAF to be a right angle triangle. In this triangle, for angle BFA, the opposite side is AB, which is nothing but small c here, and BF is BS plus SF. BS is again the circumradius, even SF is the circumradius, so R plus R is 2R. This is the sign of the angle. And from this first statement, we can write in place of angle BFA, it can be written as ACB is equal to small c upon 2R. For triangle ABC, this angle can be simply written to be angle C. So sine C is C upon 2R. On rearranging this, we can write that 2R is equal to small c upon sine C. So combining all these three, we can prove the statement, that is A upon sine A is equal to small b upon sine B is equal to small c upon sine C is equal to 2R. This is the sine rule, and if we know any three of these, we can find the other element. So only three elements are required. Say if we know two sides and one angle, we can find rest of the three. Or if we know two angles and one side, we can find. But in case we have details about only the angles, in that case, we will be able to find the ratio of the sides, but not the total length of the side. Now the right angle triangle, that is it right angle at angle A. Taken triangle is ABC, and we have this angle A, or we can simply write this to be angle A or BAC. This is equal to 90 degrees. When we draw a circumcircle passing through all these vertices, it will look like this. So in this case, the BC will be the diameter of the circle. So BS and CS are again circumradius, as S is the center of the circle. From this side angle triangle, say if we are considering this angle B, sine of this angle can be written as opposite for sine B is this small b. Upon the hypotenuse here is BC. BC is nothing but BS plus CS, so it is R plus R is 2R. On rearranging this, we can write 2R is equal to small b upon sine B. Similarly, when we consider this angle, that is angle C, for angle C to do the sine C, the opposite side is small c upon hypotenuse is again BC. BC is nothing but BS plus CS. BS and CS are R here, that is a circumradius. So on adding those two, we'll get 2R. So C upon 2R. Rearrange this, 2R is equal to C upon sine C. But for angle A, opposite side is BC, which is nothing but A. But we know that BC is nothing but BS plus CS, which are both the circumradius. So R plus R is 2R, which means that A, small a can be written as 2R, or we can simply write this to be 2R into 1. 1 can be written as sine 90 degrees, and in this triangle, sine 90 degrees is at angle A. So we'll write this to be sine A. 2A, this is A is equal to, so 2R is equal to small a upon sine capital A. Like this, we can derive for the angle A. In that angle triangle, we have seen for all the angles. Next is obtuse angle triangle. In the case of obtuse angle triangle, whichever angle we are going to consider to be obtuse, only for that we will calculate. We'll draw a angle passing from C and the circumcenter S. So it will look like this and it will touch the circle at a point. We'll name that to be D and join from D to B. Now here that chord DC is making angle DBC in the segment. So this angle DBC will be equal to 90 degrees, as this is the angle made by the diameter DC. When we look into this figure ABDC, so ABDC is a quadrilateral which has got four sides, and then we have a circle passing through all the vertices of a quadrilateral. Because of that, we can call this to be a cyclic quadrilateral. When we consider a cyclic quadrilateral and take the opposite angles, we'll have this, that is angle BDC and angle BAC. These two are opposite angles. When we add these two opposite angles, it will be 180 degrees as per the cyclic quadrilateral concept. But here, angle BDC, if you look into this BDC, and we know that this B is a right angle because of this diameter. For that, if we write the sign, we'll have the opposite side to be small a. BC is the opposite side in this triangle, which is nothing but the sine A upon DC. DC is nothing but DS plus CS, which are again R and R. So R plus R is 2R. But this angle BDC, from this on rearranging, what we'll get, angle BDC is equal to 180 degrees minus angle BAC. We'll try to substitute this. That is sine of 180 minus angle BAC is equal to A upon 2R. We know from sine properties that sine of 180 degrees any angle will fall into the second quadrant, and sine is positive in the second quadrant. For 180 degrees, sine will not change. So this is sine angle BAC is equal to A upon 2R. So BAC can be simply written as sine A. So we'll have sine A is equal to A upon 2R, or on rearranging we'll have 2R is equal to A upon sine A. In similar manner, we can derive for angle B and angle C also. With that, we are done with proving the sine rule for all different types of triangles, that is acute right angle and obtuse angle triangle. Once we know the sine rule, we'll see how to use this formula. I'll consider this example. Here we have A, B, which are the sides, and then sine A means we know the angle A here. Using that, we can find capital B is nothing but angle B. We'll take these two things, that is A upon sine A is equal to B upon sine B. What all are given? Here A is 3. Sine A is 3 upon 4 is equal to B is 4 upon sine B. Just take sine B to the other side. We have is equal to 4. Here on arranging this, how we'll get? It is 3 upon 3 into this denominator 4 will go into the numerator. We'll have like this 4. Now here we'll take the 4 to the other side, which makes 4 upon 4 is 1, which means B is nothing but 90 degrees here. We know A, B, and to calculate C, we can use that sum of the angles of a triangle is equal to 180 degrees. So we'll just find 180 minus angle A plus angle B. That will give the angle C. Once we know angle C, we can use these two things, and then small c can be found like B upon sine B into sine C. So like that we can find all the elements of a triangle. Coming to the next case, when we have two angles and a side, how to find the sides? Again, we will consider same thing, that is A upon sine A is equal to, here they have given C, so we'll take C upon sine C. Capital A is nothing but the angle, so small a is equal to C upon sine C into sine A. So C is here 7 root 3. Sine C means sine 90 degrees. Sine A means sine 30 degrees. So it is 7 root 3. Sine 90 is 1 into sine 3 is 1 by 2. So we'll have 7 root 3 upon 2 as small a. Once we know small a, we can also do for b. As A and C are given here, B is nothing but 180 degrees minus A plus C. Here 30 plus 90 is 120, so 180 minus 120 is 60 degrees. Now how to derive small b? We can take this b upon sine b is equal to c upon sine c. So from that b is equal to c upon sine c into sine b, and small c is 7 root 3. Here sine C means sine 90 into sine B means sine 60 degrees. So 7 root 3 upon sine 90 is 1 into sine 60 is root 3 upon 2. We'll have root 3 into root 3 is 3. So 7 into 3 is 21 upon 2, or this can be written as 10.5. So we have two angles on one side. From that we found all the remaining two things, two sides unlike the other angle. Now coming to the next case, here we have three sides given and then we have to find the circumradius. This first look into the greater side. Here C is equal to 13 is the longest one, and see whether it's forming a right angle triangle or not. In right angle triangle, we have the property that square of a hypotenuse is equal to sum of squares of other two sides. So here 13 square is nothing but 169, and if you see 12 square plus 5 square, it is 144 plus 25, that is again 169. Is satisfying the right angle triangle property. So this is a right angle, and in a right angle the circumcenter will be the midpoint of the hypotenuse. From that, we can tell that the circumradius is hypotenuse upon 2. That is C upon 2. Nothing will have 6.5 to be the circumradius, that is the capital R. Or simply we can take this C upon sine C is equal to 2R. As per the sine rule, we know that C is 13. So in a right angle triangle, the side opposite to the right angle will be the hypotenuse. So here small c is hypotenuse, which means the capital C vertex is 90 degrees. So sine 90 we can write is equal to 2r. Sine 90 is 1. So it is 13 is equal to 2r. From this r is equal to 13 upon 2, which is nothing but 6.25. You can analyze this in any one of these ways. Coming to the next term, in triangle ABC, if the angles are in AP, find the value of the given expression. Here, when the angles are in AP, we have to understand that the middle angle would be 60 degrees. Why? Say here AP means one angle to be X, and the other one is X minus D, and the next one is X plus D. So this is AP. So here we have common difference of D. So this is a AP thing. Say this is A, B, C. And we also know that sum of the angles is equal to 180 degrees, which means X minus D plus X plus X plus D, means we are just adding all the three things. This is equal to 180 degrees. So minus d and plus d will cancel off. That gives 3x is equal to 180 degrees, implies x is equal to 180 upon 3, which is nothing but 60 degrees. But here x is nothing but b, that is the middle angle. So the point we have to remember is when the angles of a triangle are in AP, the middle angle would be 60 degrees. That concept we are going to use here. Now we have to find this expression. We observe here it is like sine 2 theta. Okay, the formula of which is nothing but 2 sine theta cos theta. We'll use this formula here. With that, if we expand, it is like a upon c into 2 into sine c cos c plus c upon a 2 into sine A cos A. Now just take 2 outside. It gives A upon C sine C cos C plus C upon A sine A cos A. Now observe these two things, this one and this one terms, that is A upon sine A is equal to C upon sine C. A into sine C is equal to C into sine A. Then we'll have sine A is equal to A upon C into sine C. So when we have this here, A upon C into sine C, we can write this to be sine A. The other way of arranging this is we'll have sine C, here sine C is equal to C upon A into sine A. Whenever we have here C upon A into sine A, we can write this to be sine C. So now this can be written as 2 into sine A. This entire thing is sine A. This is sine C here. So sine A into cos C plus sine C into cos A. This is something like this, that is sine alpha cos beta plus sine beta cos alpha, which can be written as sine of alpha plus beta. Using this formula, we can write this to be sine of A plus C. We have 2 here. But if A plus C in a triangle, we have A plus B plus C is equal to 180 degrees. So A plus C can be written as 180 minus B. To write that 2 into sine of 180 minus B, this sine of 180 minus B means it gets into the second quadrant and sine will remain to be sine itself. So it makes to be 2 into sine B. But for B, we know that to be 60 degrees. So we'll write sine 60 degrees. So 2 into root 3 upon 2. 2 will get cancelled out. We'll have root 3 as the answer. So this expression will come out to be root 3. Now this is the next sum we have. You can try this sum using the sine rule. It can be solved. The solution of this will be discussed in the next video that's related to cosine rule.